It's quantum geometry and entanglement. So thank you.
Thank you. Well, I've taken a rather popular talk and added a few equations to it because probably most people don't know too much about this area. Okay, so topological quantum states, quantum geometry, and entanglement. So let's say the modern laws of quantum mechanics date back 100 years, and all the tests of quantum mechanics have shown them to be correct, no problems. But just because we know the laws doesn't mean that we know everything that they allow to happen, right? And what's been happening in the last 20, 30 years has been a discovery of surprises in quantum mechanics, and I'll talk about some of them. And the other thing is, there's been this merger of ideas from quantum information theory, really started by Richard Feynman back in the end of the 1950s. And when I started out working in condensed matter theory and quantum mechanics, we never talked about entanglement. We never talked about actions, we always talked about Hamiltonians. And the language of at least condensed matter physics has changed tremendously over the period I've worked in it, and we now have a lot of ideas from quantum information theory getting mixed in with what we do. So around about 1980, condensed matter theorists kind of thought they had a basic idea of everything. They had a large theory of broken symmetry phases of matter, superconductivity, and magnetism. But around that, whenever people think they know basically everything, they're in for a shock because nature and experimentalists will produce new things which we didn't dream of. And really what happened around 1980 was two different things about the same time. The main one will be the quantum Hall effect, but also I had something on magnetism. And many more kinds of topological matter have now emerged over the intervening decades, starting in earnest probably about 20 years ago. And in some sense, these are states of matter where entanglement plays some kind of important role. So since no one talked about entanglement early before that, then it makes sense that they didn't really guess what the kind of things that we would find would be. So soon after these kind of discoveries, the kind of unifying principle emerged when Michael Berry pointed out the Berry phase, or the fact that if I adiabatically vary a quantum mechanical state, in his particular case a quantum spin S orientated along an axis that would be like a Zeeman term, which would slowly be varied. Berry pointed out that when you get back to your starting point of the direction in which the spin points, the phase of the quantum wave function is advanced by an amount which is the solid angle subtended by the spin times 2s. An integer, and now we would call that integer a Chern number. So this turned out to play an important role in both understanding the quantum Hall and the spin chain effects, which I studied. And the crucial thing is it showed that you really had to take the spin seriously as a 2s has to be an integer. So in the previous period, at least in magnetism, people started from a semi-classical kind of picture, and then 1 over S was thought to act like a Planck's constant. So it was vaguely thought that magnetic properties would be continuous functions of 1 over S, where 1 over S goes to 0 in a kind of classical limit, and it just measured the quantumness. And that's okay if you have the standard kind of magnetism where the spins are all ordered along some direction. But it turns out that in these low-dimensional systems, when the spins can actually don't have long-range order, but can point over long distances can deviate from direction they started off with, you can get things that really depend on large orbits on the surface of the sphere, where you pick up the fact that spin is not a continuous quantity or classical quantity, but really is a quantum integer quantity. So adiabatic quantum mechanics consists of looking at is the problem where I have a Hamiltonian that depends on a classical parameter that the classical agent, is actually varying. And so at any moment, so we have a time evolution of this equation, but now x, this classical parameter, is varying in some way. It's controlled by an external agent. And the point will be that in adiabatic quantum mechanics, the instantaneous state of the system is assumed to stay close to an actual eigenstate of the Hamiltonian, and it has to be a non-degenerate eigenstate with an energy gap separating it from other eigenstates. So this is the condition for the quantum adiabatic mechanic evolution to work, that we, at each point in time, the absolute value of the overlap between the instantaneous eigenstate and the state has to be close to 1. And it's the absolute value because this is independent of phases. And in fact, the quantum distance between quantum states is defined this way. This is the Bourrez measure. It's probably the most quantum of different distance measures. You can put a power law lambda greater than or equal to 1 above this point to make it more classical. But this obeys the triangle identity, and it's a true distance measure. Hilbert-Schmidt would be the power 2 here. And with this adiabatic motion, we assume that at each point in time the wave function is related to the eigenstate at that time, just by a phase. And that phase we can write down, it actually looks like an action. So the first part of the phase is the part which would be like the Hamiltonian part of the action, which is just minus the energy when we integrate it. But the second part is what's called a Berry connection. And this is actually essentially a vector potential. I'll come back to that. You see it's got the Berry connection, and it's coupled to the velocity in the parameter space. Now, this parameter space, to have non-trivial behavior, you need to have at least dimension 2. And all the previous treatments of adiabatic quantum mechanics in the textbook before Berry had really only thought about one-dimensional adiabatic motion. And for some reason overlook the fact that if you have a non-trivial closed path, like Berry's, that you actually pick up an interesting phase. So it turns out the Berry connection is absolutely the precise analog in the parameter space of the electromagnetic vector potential. In fact, when you look at it more closely, the Lorentz force and the electromagnetic potential are just special cases of the quantum adiabatic system. So, for example, suppose I'm not allowing my electron or whatever it is to move around on its own. I've got an electron bound in a quantum well, and it's on the end of a rod. So I'm going to move this electron around slowly, because I have to, like as if you're moving a cup of coffee, you have to move it reasonably slowly to stop spilling it. I move the position of the quantum well around, because it's attached to this rod. I will actually find the agent, that's myself, who's manipulating it, will feel Lorentz force. And of course, in this case, the relationship between the quantum adiabatic parameters and the electromagnetic parameters is particularly simple. The energy of the system is just whatever the energy in the well is, plus the scalar electromagnetic potential times the charge. I assume this is an electron. at that point x, and the Berry connection, the vector potential-like behavior, is in fact just the vector potential scaled by E and h bar. So the Berry curvature is this quantity here, which is very important, and it's precisely the analog of the magnetic flux, and in fact in this case it is the magnetic flux, given in a Faraday-like form, which avoids you having to choose a right-hand rule. And so the force that the classical agent who's manipulating this thing feels is precisely Lorentz force. Now it's written in terms of the gradient of the eigenvalue as a function of position and the Berry curvature times the velocity. But this formula is actually quite general and applies to whatever parameter space you're in, and it's actually a very useful formula for calculating any kind of time-dependent parts of quantum adiabatic things. In fact, this formula was very useful in work I did. Other people found a formula, used this formula to find what's called the Hall viscosity, the response of a quantum Hall system to the rate of change of strain in the system. So again, it's something which involved the rate of strain, something which is proportional to a speed or velocity, and this part, of course, is a dissipationless part. This is just the part if I'm moving the system around and the energy goes up or down, I have to pump energy in or out of the system. But this part here, the second part, is like the V cross B term, which doesn't absorb any energy and allows you to deal with time-dependent things. So it's a formula that's not so well known. It was presented before in a very mathematical way, but it's very clear it's just Lorentz force in parameter space, whatever dimension that space may be. So the Berry connection has a gauge dependence, because the phase of the instantaneous eigenstate is actually undefined by the eigenvalue equation. Because if I take psi of eigenstate n and multiply it by a phase factor, it's still an eigenstate. And so this is the formula for the Berry connection. And under this gauge transformation, Berry gauge transformation, it just accumulates the gradient of the arbitrary phase. But if I go around the closed path, we pick up the Berry phase, and that's gauge invariant. And in the three-dimensional electromagnetic example, that's just the Bohm-Harold phase of taking an electron around a closed loop. So before people have kind of pointed out, especially working in block systems in free space, oh, it looks very much like electromagnetism. From a more general viewpoint, the electromagnetic formulas are just special cases of the much more general quantum adiabatic formulas. And the gauge covariant derivative in this phase, like P minus EA, is defined by taking out the part of the change of the wave function that's parallel to the original state. And so it's just this form. So it's covariant derivative. And if I now take this gauge covariant thing and just take an overlap between the gradient in direction mu and direction u of this arbitrary parameter space, we pick up what's now called the quantum geometric tensor. So before we just had the Berry curvature term here, which is the imaginary anti-symmetric part of this emission positive object. But in recent times, people have been very interested in studying the partner of the Berry curvature, which is now called the quantum geometric tensor. And this is actually a measure of just the metric derives from the distance measure, which I had further back here somewhere. This distance measure, which is basically a measure of the Hilbert space projected down into the parameter space. So this is a Hilbert space measure. And this metric is the Fubini-Studi metric, which now then gets projected down to give a metric in the parameter space. So again, there's an Italian connection here. So this is the quantum the quantum geometry or part of quantum geometry that people have been studying very recently. And it's well less, the quantum metric is certainly less well known than its partner, the very curvature. And for example, it defines a quantum speed in the parameter space. And now it tells you how far apart the states are, and the quantum speed as dimension time to the -1. So we actually find the criterion for adiabatic motion is h bar times the quantum speed has to be small compared to the energy gap between the state of it that we're holding fixed and nearby eigenstates. Okay, so before the Berry phase, quantum condensed matter only used Hamiltonian descriptions. Our field theory colleagues were, of course, using actions all over the place, but in condensed matter, we stuck with Hamiltonians. We derived them microscopically, and here's the point that the role of the spin was thought to be, the length of the spin was thought to be a continuous measure of quantumness, analogous to Planck's constant. And at that time, when I did this early work, there was an exactly known solution for the strongly quantum limit, spin 1/2, although one might actually say that spin 0 is the ultimate quantum limit. But spin 1/2 of Heisenberg antiferromagnet was known at that time to have a gapless excitation spectrum, which looked very much like the semi-classical prediction. And it was actually solved by Hans Bethe before he turned his attention to fusion in the sun. He'd accidentally guessed, he guessed he made an ansatz, he made a guess for the wave function of a one-dimensional spin-half antiferromagnet, and it turned out that his guess was 100% correct. Now, he didn't really understand why it was correct, and it's taken about 60 years for people doing very powerful mathematics of quantum groups and the like to actually understand exactly why this worked. But because it gave answers where people could calculate an excitation spectrum that looked superficially like the semi-classical picture, it confirmed, even though people knew that in one dimension quantum fluctuations prevented true long-range order, that long-range order would fall off very slowly for a large almost classical spin. People sort of believed that spin wave theory sort of worked, and it turns out that there's actually very little relation between the exact solution of the spin-half Heisenberg chain and the semi-classical limit. The excitations are not bosonic spin waves, they're actually they're something called spin-ons, which are spin 1/2 excitations. But it was initially believed at that time that the spin 1 would be essentially similar to the exactly solved spin 1/2 case, just a little bit less quantum. So around about 1981, for other reasons, actually starting from Koslov-Sauer's theory, I discovered that a spin 1 chain would have a novel state which would be gapped. And the previously understood picture was just the spins are magnetically ordered, but they're just kind of stacked up, down next to each other with no kind of quantum entanglement of any kind. And a kind of very clean version of the state I discovered is given by the so-called AKLT state, Affleck, Kennedy, Lieberman, Tasaki, where you have basically each spin 1 gets factorized into 2 spin halves, and they join hands with the spin on either side. There's a half spin on either side of each neighbor, and you get left over with the very same thing. You get a spin 1/2 degree of freedom at the ends of the chain, even though originally this was only spin 1 degrees of freedom on individual atoms. So anyway, everyone was expecting this kind of picture, which agrees with spin wave theory. There's no kind of entanglement or connection of any kind, just the spins kind of like to point opposite to their neighbors. So this was actually very shocking to the magnetism community, and they rejected it quite strongly initially, and it provoked a lot of controversy. But controversy is actually very good in science because it gets people thinking about things, there's plenty of received wisdom, like the received wisdom around about magnets going continuously as a function of spin from semi-classical to strongly quantum, that had reasonable sounding arguments that were convincing to people, and in this case the exact solution for spin 1/2, although it misleadingly convinced people of this kind of conventional picture. But a lot of very interesting work happened because of this controversy, and for example, the beginnings of matrix product states were found for this, and experimentalists devised new materials, and this is a chain of an organic chain where there's a nickel atom on each piece, so it's a spin 1 system. And eventually, it turned out that the predictions were correct, okay, and people had to accept them. But a lot of very useful things came out of this, both experimentally and theoretically, and numerical techniques, which proved very useful for further problems. So controversy is a tremendously good thing in science. So from a field theory perspective, so my original work was based on Kosterlitz-Thouless type arguments, which for whatever reason probably were not clear enough to the community or something to be initially accepted, so my paper was rejected about 3 times. It never got published actually. But in the meantime, I came up with a different argument which was probably cleaner after a discussion with Ed Whitton when I visited Princeton. And this is actually something that, so from the point of view of Lagrangian physics, which is something which was really a new thing in condensed matter at the time, we have this term which is the so-called theta term, which is, we heard Frank Wilczek mention it, it's also the central piece of axion physics, to add a theta term to the field theories, so this is a term which appears to be odd under time reversal. It's got one time derivative in it, so it's odd. But of course it occurs in the exponential form, e to the is over h bar. And because of that, this is a topological term when integrated over a unit sphere, because we've taken the order parameter of the antiferromagnet to just be a direction. And then this thing does not break time reversal invariance if this number theta is a multiple of pi. And in fact, I only became aware of this term, which field theorists had been thinking about after a discussion with Whitton at Princeton. And what you now see is a topological term. And of course, when I convert this to the Hamiltonian form, because it's linear in the time derivative, it's completely gone. So this is it turns out this is a general feature. Topological terms in the description of condensed matter systems always have some part in it. The fundamental part is linear in the time derivative, so it doesn't show up at all directly in the Hamiltonian. All it shows up is in various selection rules get left behind in the Hamiltonian. So while I discovered everything this stuff from the Hamiltonian formulation and some difference in the selection rules of different states, it's actually extremely clear in the Lagrangian formulation. And I think about this time, this really converted people in condensed matter to start thinking about action, which was something we never thought about before. Okay, so what's topological matter? So topological matter differs from ordinary matter because it's got some properties which in some sense can be related to entanglement type properties, which are described by whole numbers. Right? And states of matter, which are described by whole numbers or indices, can't smoothly change from one to another. Something interesting must happen at the boundary between topologically interesting matter and regular non-topological matter or trivially topological matter. So for example, if there was some kind of state of matter labeled with the number -2, and it was embedded in a sea of ordinary matter which labeled by a number 0, then something interesting has got to happen at the boundary. And in fact, going back to the spin chain problem, one sees that interesting feature is that at the edges of this thing, where this kind of entanglement across the system stops, you get half of a spin 1, a spin half on either end of the system. And that was the unexpected feature. And that's very typical of topological matter. Okay. So I'll come back to this meme, but in this case, the meme or the kind of underlying principle here is, suppose I have a load of people, and hands usually come in local pairs, unless you've had an accident of some kind. So if the chain of people holds hands, then you violated the theorem that hands come locally in pairs because there's a non-local separation of a right hand that can wave and a left hand that can wave on either side. And in these cases, these things contain these are the free spin 1/2s at the end of the thing. Okay. So this actually turns out to be the simplest example of the topological states of matter. But they're not just in one dimension, they go up to 2 and 3, and they have a lot more richer properties in higher dimensions, but this is something like the hydrogen. This turned out to be like the hydrogen atom for topological matter. Okay. So the quantum Hall fluids are perhaps the clearest example of such states, and they were found experimentally by von Klitzing. And he did a measurement where he measured the Hall conductance, actually measured the Hall resistance, or the Hall voltage across a sample that he put in a magnetic field. And it turns out that this was an unexpected discovery, just as, in fact, the spin chain was an unexpected discovery. I was not expecting this result, and he wasn't expecting to see this remarkable quantization of his measurement. Because, in fact, the same measurement of putting a sample with a constant current in it through a magnetic field had sort of been done earlier, except they put a sample with they put a sample in a constant magnetic field and switched the current on. But you never see this result. The crucial thing here, I'll just say this is, of course, replaced the system of units. We now have quantum units based on this. The kilogram is now defined using the quantum Hall effect. The topological nature of the quantum Hall effect took some time to become clear. It should have been clear at the beginning, because if I have electrons in a magnetic field going around a little circle, they will kind of collide with the edge, but they will go around, the edge modes will go around in a single direction opposite to the things. And it turns out that what's happening here is that when you get to the edge of the sample, you have quantization of the energy levels in the bulk. When you get to the edge of the sample, the orbits are reorganized by the collisions, and the Fermi and the states at the boundary can go up in energy, and the Fermi level can be, as long as the Fermi level is anywhere in this regime, we get this quantum Hall effect with a gap in the bulk. Okay, what's happening? Move on. So the remarkable thing about the quantum Hall effect is what's called a Schrader anomaly. Rather than the original measurement, there's the precise relation between the current and the electric field. There's a much more richer relation between the charge density and the magnetic field, written as a Faraday tensor. Because without the edge states, this would tell you, this is saying I've got a system with a gap, I change the magnetic flux through the system, and the density of electrons changes. That would be an obvious violation of gauge invariance and charge conservation if it wasn't for the one-way edge states, which allow the states to flow down and become populated as they go through the Fermi level. So the integer Hall effect was soon followed by a much bigger puzzle, the fractional Hall effect. And there was this remarkable wave function which was again discovered semi-accidentally by Laughlin, who did a numerical three-body calculation for other reasons and found out and was able to notice the low energy state, which was z1 minus z2 to the cube. And anyway, so this is a very interesting state, which is for m not equals to 1, it's not a Slater determinant state. And this marked the end of the dominance of diagrammatic perturbation theory. Before this state, everyone in condensed matter, and probably in field theory too, maybe not, sort of thought that all problems should be solved by diagrammatic perturbation theory. Diagrammatic perturbation theory is only good if you've got a Wick theorem, a kind of non-interacting state or a harmonic oscillator state to start with. And this state is that m not equals to 1 does not obey Wick's theorem. There's no basis for diagrammatic perturbation theory. And for example, the Russian school at the Landau Institute, who are the kings of Fermi liquid theory and diagrammatic perturbation theory, are basically unable to make any contribution to this problem of the fractional Hall effect because it was something that you could not tackle with diagrammatic perturbation theory. So it showed that you have to develop methods which work for each kind of problem. The topology of the thing is seen that this the result was seen in a piece of equipment looking like this, which would certainly, if you submitted this as evidence of your soldering ability, it would not get you a job at Intel, right? But because of the topological nature of things, it suffices to have a piece of equipment that looks like that to see the forgiving nature. Okay, I should move on very quickly. This was confirmed to work. Numerical methods like exact diagonalization of finite systems turned out to be very important in showing this was actually the correct solution to the problem. And there's some problems there's a toy model for which this is the exact ground state. So Laughlin's state has been the fundamental source for interpretation of the fractional quantum Hall effect. And a popular idea has been a notion of so-called flux attachment, a kind of hand-waving notion to describe things. Now, it turns out that, I'll move on very quickly, this was for many years, we only had this in Landau levels, which are the time magnetic flux. But starting around 2011, and last year, I guess, experimentally, we now know that the fractional quantum Hall effect can occur without a magnetic field, only with time reversal braking due to ferromagnetism. And, okay, probably you shouldn't. So, it was a toy model. A toy model was for the integer Hall effect without magnetic fields. Was emerged in the 1980s. But it took a long time for it to actually be realized experimentally. This is actually a graphene-like model with second neighbor interactions with British time reversal. And this model was recently, 10 years ago or 12 years ago, shown to also support a fractional Hall effect when you made the bands very flat and had impulsive interactions between them. And now the experimental system, which is very people are very excited about these days, is these so-called moire patterns you get with twisted bilayer graphene, and there you can get by tuning the angles, you can get extremely flat bands, which are needed for the interactions to dominate kinetic energy terms, usually these non-trivial states. Okay, so let me just move on very quickly. So one thing in these things which is in Landau levels turn out to be very useful is that we can separate out the coordinate into a Landau orbit around a point which is described by the guiding center of the orbit. And what's actually happening, the orbitals move, and what's moving around is the guiding centers. But when you start off with commuting geometry, where x and y commute, and you separate it out into two parts, and quench the kinetic energy, which is the Landau orbit, you end up with non-commutative geometry, which is the key to understanding a lot of these properties, which I guess. So let me just quickly move on now, since I've run out of time. I would say just my one point, I guess, of my own current work is to try and understand how the Lofton state can generalize to systems with no magnetic field. And the key idea is that in the Landau level, there's one orbital per unit of magnetic flux through the system, but the Lofton state, basically, at 1/3, every electron occupies 3 orbitals. And so the new language I'm pushing for this is orbital attachment rather than flux attachment. Let's move on quickly. So this is actually leading to practical stuff. So the Lofton state was interesting, but more interesting are so-called non-abelian quantum Hall states, which are discovered by these guys, and Alex Kiteev pointed out they could be very useful for topologically protected quantum computation. And again, there's an Italian connection with Majorana. Let me just move through. So in this case, the excitations of these objects, which were just interesting objects with fractional charge in the Lofton case, turned out to be something like half of an electron orbital. Majorana zero modes. Majoranas are not fermions, it turns out. The Majorana we talk about a half of a fermion, or a Majorana zero mode, and the fermion was really an orbital that can accommodate an electron, which has been separated into 2 half orbitals, a remarkable idea. So let me go forward to the end of this thing. So in this case, I have defects or topological defects which you can't create by themselves, but you can you could create a double defect by itself and pull it apart into 2 halves. And each of these halves is really half of an electron orbital. So this object could either be containing an electron or not an electron. So it would either have fermion number 1 or even or odd fermion parity. But once you pull it apart into 2 half things, which are connected by an entanglement string, you can no longer tell whether the object you pulled apart was even or odd fermion parity. So the fermion parity is hidden in these entanglement strings. And now when you start to braid these ends through each other, you mix up the entanglement pattern, and this is where the quantum information is stored. So the elementary unit is for 1 qubit would be 4 of these things, because fermion parity you can't mix states of even and odd fermion parity. But this has 2 even states and 2 odd states. So whatever the parity is, there's 1 qubit in. And this is actually what's been proposed by Microsoft for their Majorana 1 proposed qubit, although we're not sure that they've actually managed to create the working one. So I guess, so by braiding these things around, the initial conditions are what I pulled the things apart, and the initial conditions become hidden by pulling them apart into half objects, which leave their quantum information in these strings, and by braiding them around each other, this could be the qubit pointing up. This would be a state, for this case it's a qubit pointing in the equatorial plane, and by mixing around you can move the qubits around in principle. Okay, that's a picture of the hidden information only is hidden until when things are very close together, the information starts to become revealed again by interference patterns. So this topological stuff only works once you've separated everything to be further apart. The half orbitals or the Majoranas have to be further apart than the decay length. And that's the current problem in the attempts to make physical realizations of these things. The question is, can you make them separated enough? So entanglement is only interesting if you entangle if it's over scales which are large compared to the microscopic scale. But this is what people are working on. So this is actually 2 states of a qubit, and you see there's little waves because they're close together, there's little kind of different interference patterns which would tell information. So this all came up from Majorana, who vanished in 1937, and he, of course, had a rather different vision. He had a field theoretical vision of splitting the Dirac equation into real parts. But essentially, in the condensed matter thing, we've got the Majoranas are the half of an orbital. There's a spin-orbit coupling, so the orbital is either empty or filled, and you can't put a second electron in. The spin-orbit coupling determines which kind of spin direction you put into it. Let's quickly skip that. So in a superconductor, this is a model which Kitaev wrote down. You could have, this is electron hopping on a chain with a proximity effect, superconducting effect induced by a nearby superconductor, which gives you creation or destruction of pairs. And by writing these in a superconductor, the charge of the electron gets taken off it and lives on the outside surface of the superconductor, and you can write the creation operator as a pair of real fermions, which are really half of the fermion, the Majoranas. And of course, what's only interesting if you can separate these things to be physically separated. So in the superconductor, you sort of start off with the Majoranas, which are really formal, but then with the superconductor, you manage to make them recombine with the A and the B halves on their neighbors, and you manage to physically separate these two half orbitals at a distance away from each other, which is mesoscopic at least. And this is so this is actually almost like the original spin chain and the picture of people holding hands, but now it's a much more remarkable factorization of an electron orbital into two half orbitals. Okay, and I think I'm way out of time, but let me see. Okay, so I guess this is only one of the approaches to qubits. Other qubits have been much more successful, but we're hoping that notionally this is a much more scalable thing. Now, of course, on paper this thing works tremendously, and we're still really waiting to see if Microsoft has actually managed to make the decay length long enough so the things become truly independent. And of course, fusion works tremendously well on paper too, and we're still waiting for fusion. But this is something that is possible, and I personally believe it's a realistic dream that we will eventually have topological protected computer. On the other hand, it may well be that error correct. This may just be the inspiration of good error correcting codes and things for regular qubits. But anyway, so this is some of the remarkable things that quantum mechanics have made possible that we wouldn't have dreamed about 100 years ago. And so we haven't changed the rules of quantum mechanics, but we're discovering it's got really, really crazy but cool things can happen. And there we are. Thank you.
Professor Haldane for this wonderful overview on quantum mechanics applications. And so we have time only for one, maximum 2 questions.
Thank you very much for the exciting talk. I will try to ask the simplest of all my questions. So in the beginning of the slides, you showed a Schrodinger equation where on the right-hand side, have included this function of classical variables. I'm wondering, how do you deal in the system time reflection? Because in quantum mechanically, time is a parameter. So on the left-hand side, when you apply time reflection operation, it's anti-unitary. But there is a classical x of t.
The Hamiltonian had a classical variable which you control. So you have, it's like a video game. You have a joystick and you move it around. And in the simple example, what we were moving around was just a quantum well on the end of a rod. Now you move that very slowly, so your motion doesn't cause a transition between the levels. If you had a coffee cup in your hand and you do that, the coffee will kind of spill everywhere. So you have to kind of do it slowly. But interestingly, the the Lorentz force and everything translates into this general thing. You as the operator, or the classical agent, I mean, it could be, it doesn't be you, I guess. Some classical agent is causing this, this motion, and the forces on it are not just the direct forces where you have to do work on the quantum system to change the energy level and keep it in the eigenstate, but you also experience this sideways force which is measured by the Berry curvature. So it's actually quite a surprising thing, and it's actually not such a well-known thing, the quantum Lorentz force, and it turns out to be very useful for various kinds of calculations.
Okay, so probably we leave more questions for the question time after this session. Let's thank again Professor Haldane.